Hello all and welcome to my talk on the one-sided transposition shuffle. I'd like to take a moment first of all to thank the organisers for allowing me to speak and say that all the work I'm presenting here is joint work with Michael Bay and Stephen Connor from the University of York. So what is a one-sided transposition shuffle? Well, it's a random walk on the symmetric group which we can view as a deck of cards. At time t, we will choose a position j uniformly at random with our right hand. Then we will choose a position I uniformly to the left of our right hand. So we cannot choose any positions over here, and this is exactly what makes our shuffle one-sided. Once we've chosen our positions, we're going to swap the cards in the given positions. Okay, this is exactly like applying the transposition ij. And in fact, as a probability distribution, the one-sided transposition shuffle is denoted Pn. So we don't just want to look at how the shuffle acts after one shuffle, we want to see how our deck looks after t of these shuffles. And we shall denote the distribution of our deck of cards after t shuffles as Pn to the power t. As t tends to infinity, our deck is going to tend to be uniformly random. So as we shuffle and shuffle and shuffle, we're getting closer and closer to uniformly random, which is what we want. We want to also measure how close our deck is to uniformly random, and we do this using total variation distance, which is 0 when the probabilities are the same and 1 when they're totally different. Now that we can measure how close our deck is to the uniform distribution, we want to know how fast this convergence happens. And it's possible to get generic bounds on the convergence of any random walk using theorems from Markov chains. However, for any particular example, we can find a much tighter bound, with the overall goal being to prove a cutoff. A family of random walks exhibits a cutoff if we can find a time tn such that if we do tn steps, and then a few more, we are very close to uniform. But if we do tn steps and then a few less, we are very far away from uniform. It's really trying to encapsulate the idea that convergence to uniform happens in a short time frame and window. If that definition was too fast for you, just look at this graph. Okay, the random process in red here shows a cutoff because it stays close to 1 and then converges to 0 very fast once a certain time has been met. The blue line does not show a cutoff because although it converges to 0 fast, it does not stay close to 1 for a long time. So we want to prove a cutoff for the one-sided transposition shuffle. That's what my talk says. Okay. To do this, we need to do two things: to prove an upper bound on total variation distance and a lower bound on total variation distance. In fact, in this talk, we're only going to be focusing on the upper bound, and we are going to use algebraic properties of the symmetric group and our shuffle to recover a unique description of the eigenvalues for the shuffle in terms of Young Tableaux. Why is covering the eigenvalues so important? Well, if we know the eigenvalues for the one-sided transposition shuffle, which all lie in the range 1 to -1, we can bound its total variation distance to the uniform distribution as follows. So it's a sum of the eigenvalues to some power. So once we know the eigenvalues, we can then just apply some analysis to this bound to find the correct time t. And we want to find a time t such that the right hand side is bounded in n. And this will give us the correct time for our cutoff. So now we have to focus on finding the eigenvalues. How do we do this exactly? Well, to find the eigenvalue, we first of all need to find the eigenvectors. And our first step is to change our viewpoint. So instead of thinking as the shuffle Pn as this probability distribution, we're going to start thinking of it as an element of the group algebra denoted Qn. To form Qn, we just take a linear sum of every transposition times its probability of being applied, and then we scale by n to make our calculations easy. I don't want you to get confused. Qn and Pn really do denote the same shuffle, just viewed from two different angles. And in fact, we can see this as we can say that the eigenvectors and eigenvalues of Qn acting on the regular module of our group algebra are in one-to-one correspondence with the eigenvectors and eigenvalues for the shuffle Pn. So they really do behave the same way, and the eigenvalues for one give us the eigenvalues for the other. This hasn't reduced our problem at all, it's just changed our viewpoint. However, we can now reduce our problem because the regular module can be decomposed into simple modules, and these are much smaller in dimension. So instead of studying the action of Qn on the entire regular module, we can study the action of Qn on each individual spec module. This is the first step to finding our eigenvectors. Okay. Each spec module or simple module is denoted by a partition event. A partition event is just a decreasing tuple that sums to n, and they are often denoted by Young diagrams. A Young diagram is just a left-adjusted stack of boxes such that we read the tuple, and the value in the tuple, the value in position 1 of the tuple gives us the number of boxes in the first row, value in position 2 gives us the number of boxes in the second row, etc. So each spec module is labelled by a partition. So we are going to talk about eigenvalues and eigenvectors belonging to partitions instead of spec modules, as this will just simplify things. Okay. The key to finding our eigenvectors is the idea of lifting eigenvectors, which was recently discovered by Breek and Scholer when they studied the random-to-random shuffle. What lifting eigenvectors does is it allows us to turn eigenvectors of our shuffle on n cards into those of n plus 1 cards. And this recursive structure comes from our shuffle and the symmetric group together. Okay. And in fact relates to Young diagrams and partitions. So given our partition on the left here of n boxes, we can turn it into partitions on the right of n plus 1 boxes by adding a box on a row of our preceding partition. So we add a box to row 1, we form the partition at the top here. If we add a box to row 2, we form the middle one. If we add a box to row 3, we form the bottom one. Okay. So this has nothing to do with our shuffle at the moment. It's just we can turn partitions of n into partitions of n plus 1 in this descriptive way. Now what lifting eigenvectors tells us is that if we have an eigenvector belonging to the partition on the left, we can turn it into an eigenvector belonging to partitions on the right. So notice here that our shuffle and the structured symmetry group are really interacting here in this unique way. And this is the key slide of the talk. If there's nothing else you take away, I want you to take away this picture. So not only do we know we can turn eigenvectors into eigenvectors, we can also understand how it changes the eigenvalue at each step. Given an eigenvector v of our shuffle on n cards with eigenvalue epsilon, then LIV is an eigenvector of n plus 1 cards with eigenvalue epsilon plus this fraction. Okay, so now we could just really forget about the eigenvectors if we wanted and concentrate on the eigenvalues, as these are what we need to bound our total variation distance. So the partition 1, denoted by a single box, gives us all the eigenvectors of our shuffle on 1 card. We can easily compute these, because it's just a 1-by-1 transition matrix. Once we have this, we can then use our inductive process, lifting eigenvectors, to find the eigenvectors belonging to partitions with 2 boxes, and then 3 boxes, and then 4 boxes, etc. In this way, we can recover all the eigenvectors and eigenvalues for the one-sided transposition shuffle. And in fact, if we take a path down this diagram, which is called Young's lattice, ending up in a partition, the path we take really matters, because each different path we can take gives us one distinct eigenvector for our shuffle. So here the red path and the blue path give us different eigenvectors belonging to the partition 2, 1, 1. And in fact there is a third path where we change from blue to red in the middle. Okay. So each path gives us a distinct eigenvector, therefore a distinct eigenvalue. We know all the eigenvalues can be recovered, we just need a way to talk about them and label them. To do this, we're going to resort to using standard Young tableau. A standard Young tableau is a Young diagram with the numbers 1 to n in its boxes such that each value occurs once, and they are increasing left to right and top to bottom. All the standard Young tableau of the partition 3, 2 are given here. Each standard Young tableau defines one path down Young's lattice that starts at the empty set and ends at lambda. How do we define this path? Well, you add the boxes to the empty set in the order given by the tableau. We add box 1 first, then box 2, 3, 4, and then 5. Now, because each standard Young tableau denotes one path down Young's lattice, it therefore denotes one eigenvalue and eigenvector for our shuffle. So every eigenvalue for the one-sided transposition shuffle is indexed by a standard Young tableau, and furthermore, each eigenvalue occurs with multiplicity the dimension of the partition. So given an eigenvalue associated to, or given an eigenvalue denoted by the standard Young doublet T, its eigenvalue is 1 over n times this sum. Each single element of this sum is really just one of the changes we saw on a previous slide. We just sum all the changes and then divide by n, because at the start we scale Qn by n. Okay, so now we have all our eigenvectors. This is wonderful, and it means we can apply the theorem from the start. That says that our total variation distance is upper bounded by a sum of these eigenvectors. All that's left to do is find the correct time for our upper bound for the cutoff. And the correct time is n log n. So at time n log n and a few more steps, where a few more of it in this case is plus an extra constant of n, we can find that the total variation distance to uniform is not only bounded in n, it is decaying in C, which means that as we do more and more steps, we're going to be tending to 0. So this is our upper bound complete. Now I said we weren't going to talk about the lower bound, we will do briefly. So the one-sided transposition shuffle also satisfies the following lower bound that says that at n log n and a few less steps, we have it lower bounded in n. Okay, and as C tends to infinity here, we get this tending to 1. Putting these two results together gives us that the one-sided transposition shuffle exhibits a cutoff at time n log n. This is twice as slow as the classical random transposition shuffle, which exhibits a cutoff at time n over 2 log n. Okay, further details of lifting eigenvectors and the upper bound, as well as a full proof of the lower bound, can be found in our paper called Cutoff for the One-Sided Transposition Shuffle and the archive link is here. Thank you very much for listening.